are suddenly decelerated upon collision with metal anode target, which usually made from tungsten or molybdenum. This is a picture of X-ray tube. It's a vacuum diode where X-rays are produced. X-rays are produced here in this tube, and this is a filament where electrons are emitted, and this is the metal anode target. This is metal anode target. And this figure shows the process of X-ray production. When cathode filament is heated by an electric current, it emits electrons. And these electrons are accelerated by high voltage generated by high tension transformer. When high speed electrons hit the metal anode target and suddenly decelerate, X-rays are produced. Usually in this process, most of the electrons beam energy becomes heat, and only less than 1% of it becomes X-ray. And this will result high temperature in the anode target. Remember the substance used for the making of anode target? The tungsten or molybdenum. Both of them have high melting point. And the target area of anode is usually set in copper, which is a very effective heat conductor. And these settings are helpful in avoid melting of anode target. Now let's talk about the characteristics of X-ray. X-rays has 4 important characteristics. The first one is penetrating effect. It means X-ray can penetrate through an object, but this is accompanied by a partial absorption, which is called attenuation. The higher voltage the X-ray tube is applied on, the shorter wavelengths and the produced X-rays will have, and the stronger penetrating effect it will possess. The penetrating effect of X-ray is also relative to the thickness and the density of examined object. The thicker and denser an object is, the more X-ray will be attenuated. And the penetrating effect is the foundation of X-ray imaging. The second characteristic of X-ray is the photosensitivity. When a piece of film covered by a layer of silver highlight is irradiated by X-ray, the chemical structures of exposed silver highlight grains change and forms a latent image on a film. So the process of development and fixation, the latent image will become visible due to the deposition of metallic silver particles on the film, which come from the exposed silver highlight grains. The amount of disposed silver particles is inversely proportional to the absorption of X-ray. And the photosensitivity of X-ray is the foundation of radiography. Fluorescent effect. This effect means X-ray can excite the fluorescent material and generate long-wave visible light, called fluorescence. It is the foundation of fluoroscopy. The first characteristics of X-ray is ionizing effect with the biological effect. In short, X-ray can make the molecules ionized and break down the structure of molecules. The ionizing effect of X-ray is the foundation of X-ray radiotherapy and also the reason for medical radiation protection. It's harmful to human body. So the ionizing effect of X-ray is also the reason for medical radiation protection. Now let's talk about principles of X-ray imaging. The essential factors of X-ray image formation can be divided into the following three types. The first type is about characteristics of X-ray, including its penetration effect, fluorescence effect, photosensitivity, which have already been talked about by us. The second type is about the characteristics of exam objects with different density or thickness. Object with different density or thickness will cause different X-ray absorption or attenuation. The third type is about visualization of X-ray image. To make X-ray image visible, you need either X-ray film or fluorescent screen. The fluorescent screen is covered with a layer of fluorescent material. Let's see how density and thickness of exam object influence the formation of X-ray image. The attenuation of X-ray is proportional to the density or specific gravity of exam object. And this attenuation of X-ray is reflected as grayscale on radiograph and brightness on the fluorescent screen. Here are two X-ray film which are unexposed to X-ray and exposed to X-ray respectively. The latter is obtained without any exam object between the film and X-ray tube. After development and fixation, the film unexposed to X-ray looks white, and the film exposed to X-ray looks black. Now let's put something between the X-ray tube and the film or fluorescent screen, and see what happens when the same X-rays penetrating objects, the three objects with same volume and different densities. The object with highest density is on the left, with lower density on the right, when the medium density in the middle. Remember, I have said that the attenuation of X-rays is proportional to the density of exam objects. The higher the density of the exam object is, the more X-rays will be attenuated, and less amount of X-rays will be residual after X-rays penetrating the object. So the residual amount of X-rays is smallest after they penetrating through the object with high density. In contrast, the residual amount of X-rays is largest after they penetrate through the object with lowest density. And the amount of X-rays after penetrating through the object with medium density is in between them. The residual X-rays will strike photographic film or fluorescent screen positioned on the other side of the object. On the film, the image of the object with highest density with high density will look whitest. An image with of the object with low density will look blackest. An image of object with medium density looks gray. And the appearance of these objects on the fluorescent screen adjust object to their appearance on the field. Why? Just think about it, and I will tell you later. This slide shows the radiographic appearances of materials with different densities, which are inside the test tubes. These materials include barium sulfate, chalk, contrast agents with iodine concentration of 76% and 16%, water and air. The image of the barium sulfate, which has the highest density here, looks brightest. An image of air, which has the lowest density here, looks darkest. An image of the contrast agent with iodine concentration of 76% is more bright than that with iodine concentration of 16%. It looks more bright. This one looks more bright than this one. Okay. And this one the brightest here, and this one the darkest here. And different tissues in human body have different densities and allow different amount of X-rays to pass through. During X-ray examination, their corresponding areas on a film will be blackened in varying degrees, depending on the intensity of the radiation that has passed through them and reached the film. Bones, for example, permit few X-rays to penetrate because of their high density and high density of calcium content. Therefore, bones appear white on the film. And soft tissues such as spleen or kidney allow moderate amount of X-ray to pass through and usually looks gray on the film. Moreover, these tissues are not well differentiated from the surrounding tissues because they permit just approximately about as many X-rays to pass through as to the surrounding tissues. The organs filled with air, such as lung, appear black on the film. This is an X-ray film. This is an X-ray film of lumbar spine. You can see the lumbar spine, part of sacrum, and the bilateral ilium, and also some ribs, and they all appear white. They all appear white. The psoas muscle here, the psoas muscle appear green. Can you find the bilateral psoas muscles? They are triangular in shape and just adjacent to lumbar spine. Here, a psoas muscle. Here, a psoas muscle. Here, they are triangular in shape and just adjacent to lumbar spine. Do you know what is this black area? Do you know what is this black area? They are air within the intestines. They are within intestines and stomach. Maybe you have a question. This is X-ray film of lumbar spine. Why is air within the intestine and stomach are displayed? Because all body tissues and organs penetrated by X-ray will be displayed on X-ray film if they cause enough difference of attenuation of X-ray from surrounding tissues. The lumbar spine is in the back of the body. This X-ray film of lumbar spine is obtained with X-ray penetrating through the body from anterior to posterior. Stomach and intestine are in the belly. When they are filled with air, the attenuation of X-ray result from them is much less than the surrounding structures, which make them appear as black area on the X-ray film. And this is the chest film. Lungs, bilateral lungs, just bones, ribs, clavicoscapular, and the heart, which is an organ of soft tissue. Also, you can see the lungs, just bones, and the heart. And this heart, it's organ of soft tissue. It also looks white. Why? It's not look green, but it looks white. Why? It's mainly because of the thickness of the tissue. Now, let's see the actual imaging of tissues with different thickness. Different tissues in human body have a different let's say how thickness of the examined objects influence their appearance on the film and the fluorescent screen. The tissue within human body have different density, and they also have different thickness. I think it's easier for you to understand that the thinner part of an object will absorb less X-rays than the thick part, and therefore appears more black on the film and more bright on the screen. And same thing happened for this object with triangular shape. The thinner part, the thick part. The thinner part looks black on the film and bright on the screen. And for hollow cylinder object, its rim is thicker than the center, and therefore its rim looks whiter on the film and darker on the fluorescent screen. And this is the X-ray film of a long bone shaft. This long bone is the fibular. It's a long bone. In the center of this bone shaft, there's a medullary cavity, which is filled with bone marrow. The density of bone marrow is much smaller than that of bone tissue. Therefore, the structure of a long bone shaft is similar to a hollow cylinder object. And on the X-ray film, its center appears blacker than the rim. The rim looks bright. The center looks gray. It's blacker than the rim, right? Because this bone shaft is just like a hollow cylinder object. Do you have an answer about the question? I've just asked you why the appearances of the same object on fluorescent screen is opposite to its appearance on the film. This slide shows the difference of fluoroscopy and radiography. Let's see the appearance of chest on the fluorescent screen and X-ray film. On the fluorescent screen, the lungs appears white and the heart appear black. In contrast, on the film, the lungs appear black and the heart appear white. Their appearance on the film are just opposite to their appearance on the front screen. Why? Because the fluoroscopy based on the fluorescence effect of X-ray. X-ray can excite fluorescent material on the front screen, and generate long visible light. The more X-ray reaches the screen, the brighter the examined tissue appears. In contrast, radiograph based on the formation of radiography is based on the photosensitivity. The more X-rays reach the film, the more several particles are produced, and the exam tissue appears. And this is the reason why the appearance of same object on flat screen is opposite to its appearance on the film. The penetrating effect of X-ray also has influence on the quality of X-ray film. On a test film with normal penetrating effect of X-ray, the target tissue, for example, in the chest film, the target tissues are lungs, heart, and lung markings, and this tissue are clearly displayed, and there are good contrast between them. You see the contrast between the lungs, airfield space of lung markings, and heart. The contrast between them are good. You can observe the contour of these structures clearly. The penetrating effect X-ray influenced by the voltage applied on X-ray tube. The higher voltage X-ray tube applied on, the stronger penetrating effect it will have. When the voltage used is too low, the X-ray will become weak, and it may be blocked by tissues that it normally can penetrate through. And all these tissues will appear white on the film and lose their contrast, and some of them cannot be discerned. And on this chest film, with the added penetrating effect of X-ray, you see the lateral zone of bilateral lung field appears white, and the costal phrenic angles cannot be discerned. So, but what happens when the voltage is too high? When the voltage use is too high, the X-ray will become very strong, and the amount of X-ray that pass through the exam body area and reach the film are more than those with normal voltage. And the image of the exam area on film will be darker than that occur with normal voltage. The contrast between tissue, the contrast may be reduced. However, a proper increase of voltage is helpful in examining the lesions, examinations with high density or lesions covered by adjacent high density structures. Look at this X-ray film. The area indicated by the arrow is a lesion of consolidation in the left lung field. Airspace of this region of lung is filled with inflammatory acute. Its density is higher than the normal pulmonary tissue containing air, and the detail of this lesion is well displayed, although it's covered by the ribs because the high voltage is used. And the radiograph has some shortcomings. And this picture shows the method. This picture shows the method of X-ray examination. This is the tube. This examines the human body, and on the far side of the human body, there is the film. Here is the film, the cassette containing film. By this method, you can obtain a two-dimensional image of a three-dimensional subject. On this image, there are overlapping shadows of various tissues and organs. And if there is a nodule in the lung field, chest film of anterior posterior view, we cannot be sure whether it is outside or inside the lung, because the nodule on the chest wall may cause the same finding as the nodule inside the lung. To solve this problem, you need a lateral projection. And the way of X-ray examination will also cause magnification. And the shorter the distance between the film and examined object, the lax magnification will occur. In addition, the way of X-ray examination will also cause distortion of image. When the relative position of X-ray tube and examined object changes, you will have different image, just like the human figure, under the sign. You see, when the position of sign and the human body changes, you have different figure. You have different figure of human body. Okay, I think this is easy to understand. The sun is here, and the human body here, and it got a figure like this. And when their position change to this way, you have the human figure like this. Now let's talk about the equipment for X-ray imaging. The first group of equipment is X-ray production devices, including X-ray tube, transformer, and a control table. And this image show you the equipment for X-ray production. This is X-ray tube. And this is the transformer used to. This X-ray tube used for generate X-rays. This transformer used to change voltage. And this is the control table. And the technician can use the control panel on it to adjust the parameters of X-ray machine so as to get X-ray film with good quality. See, this X-ray tube. This is a patient. The cassette containing film is here. And the second group of equipment of X-ray, the second group of is X-ray detection devices. Conventionally, it includes X-ray film and a fluorescent screen. Both are analog detectors of X-rays, which means that their response to a steady and continuous increase in radiation doses is also steady and continuous. It's opposed to stepwise. On X-ray film, images of exam subjects appears shadows of varying degrees of blackening, which is determined by the density of deposited microscopic black silver grains. Fluorescent screens show the image of exam subject by emitting visible light. To make image on screen not only visible but clear and convenient for observation, people use imaging intensifier plus TV technique in fluorescent examination. And the conventional radiography has to use a lot of films. It's a resource wasting and not good for environmental protection. And the storage of this film is also a big problem. You need a big room to place them, and if you want to see a film taken 3 years ago, it may take you a long time to find it. And seeing all these shortcomings of conventional film-based radiography, people develop computed radiography. In computed radiography, following exposure to X-rays, special imaging plates is used to retain a latent image of stored energy. By scanning the imaging plate with a laser beam, the energy is released as light or luminescence, where the light intensity is proportional to the absorbed dose of X-ray photons. The emitted light is recorded by a photodetector as analog signals, which are digitized later. The image may be presented in a grayscale format on a monitor or hard copied by a laser printer. These slides show the equipments and the workflow of computed radiography. X-ray tube. The X-ray tube emits X-rays which penetrating through exam subject and strike the special imaging plate. This imaging plate receives energy from X-ray reaching it and form a latent image. And this latent image is read by laser beam and transformed to a digital image, which can be displayed in a grayscale format on a monitor or printed by laser printer, or saved in picture archiving and a communication system. So this picture archiving and a communication system, this image can also be accessed by other computers. These are the equipment and the workflow of CR, computer radiography. And compared with the conventional film-based radiographies, computer radiography has following advantages. First, the digital image obtained by CR can be archived in disks and saving space of keeping film. Second, the digital image can be communicated through network. Third, the digital image is easy to be post-processed and manipulated. You can change the contrast, grayscale, and the size of the images, and you can also measure the distance between two different regions on the film or calculate the areas. The disadvantage of CR compared with conventional radiography is that its spatial resolution is inferior to full-size radiographs due to the relatively large pixel size. Later people further after CR, later people further developed digital radiography system. In digital radiography system, flat panel detector is used to convert X-rays into electricity directly or indirectly. And this electricity is captured and transformed into image with reading device. And compared with CR, DR can save some middle processes before obtaining images, and therefore can improve the workflow. And this picture shows the sense of performing DR examination for a patient using DR. Image data is available immediately for display on a video monitor for technologist review. If the technologist finds the quality of the image is not good enough for analysis, he or she can do examination for patient again immediately. In contrast, if you ask patient to come back and do examination again after patient has leave, there will be a lot of trouble. And then DR can help us avoid the occurrence of this trouble to a certain degree. Now let's talk about radiographic examination techniques. As you already have known, based on the imaging display method, there are mainly two types of radiographic examination techniques: radiography and fluoroscopy. The former display image on the film, and later display image on the screen. Nowadays, commonly used techniques for radiography include ordinary projection with tube voltage run from 40 to 100 kV, and high kV projection with tube voltage higher than 120 kV, and soft tissue projection projection with tube voltage smaller than 40 kV. And sometimes we use contrast agent to make the target organ be displayed clearly. And this involves use contrast examination. Let's talk about them one by one. Look at these two images of chest. This one is ordinary radiograph. It's a high kV radiograph. You can find that the high voltage radiograph display the trachea and the retrocardiac lung markings more clearly than ordinary radiograph. Right? You can see the lung markings in the retrocardiac area, but you cannot see them here. And also the trachea is displayed much more clearly on high kV radiograph than ordinary radiograph. Why? Because the shadow cast by high density of bones or thick structures like heart are reduced by increasing the voltage. So the high kV radiograph is very useful in this for these settings. They can reduce the influence of the shadow caused by high density of thick structures. So the other structures inside or behind them will be displayed more clearly than ordinary high kV radiograph than on ordinary radiograph. Soft X-ray projection are mainly used for breast X-ray examination called mammography. And this technique uses a low kV and molybdenum target to produce long wavelength X-rays, which is called soft rays, so as to achieve high spatial resolution and a maximum contrast between the soft tissue component in the breast. And these are two examples of mammography. These two X-ray images show the carcinoma and hyperplasia of breast respectively. Okay, it's time for rest. You have 10 minutes for rest, and let's continue our class 10 minutes later. We will start the next class at 8:55. Okay, see you later.